Another specific example of integration being applied is kinematics. From differentiation, you may remember that if we derive or find the derivative of displacement, we get velocity. And if we find the derivative of velocity, we get acceleration. Now that we know that integration is the opposite of differentiation, we can actually go backwards. So we could start off with acceleration and get velocity, and then we can integrate velocity to get displacement. Now displacement is represented by x of t, velocity is represented by v of t, and acceleration is represented by a of t. Let's jump into a quick example to see how these are applied. In this example, a ball is thrown vertically upwards from a 30-meter high cliff at a velocity of 15 meters per second. And we're asked to assume that gravity is equal to 10 meters per second squared. Part A of this question asks us to calculate the acceleration of the ball in meters per second squared. Now, in a normal situation, when you have a projectile or something going through the air, the acceleration is generally only caused by gravity. So in this case, a of t is just going to be negative 10 meters per second squared. Now, I've done negative 10 instead of positive 10 because when I do kinematics questions, I like to assume that downwards is negative and upwards is positive. This makes the most sense in my mind, but as long as you keep it consistent within a question, then you're all good. Now, part B, it asks us to find the velocity, v of t, of the ball in meters per second. So what we do to get velocity is we have to integrate acceleration. So we have to integrate negative 10 dt. So what we get is negative 10t plus c. Now, we shouldn't leave plus c in our equation because this is a specific example, and having a plus c on the outside of velocity doesn't really make much sense. So what we have to do is we have to substitute in a piece of information to help us find the c. In this case, that piece of information is going to be the initial velocity of 15 meters per second. Initial velocity meaning that it's at time is equal to 0. So v of 0 is equal to 15. We can substitute that in to get 15 is equal to negative 10 times 0 plus c. So we end up getting 15 is equal to c. Therefore, v of t is equal to negative 10t plus 15. And it's good practice to specify your unit as well. In this case, it's meters per second. I didn't mention this at the start of the question, but the units for kinematics are really important. We started off with meters per second squared, and you might notice that this is meters per second. So we're not jumping from meters per second squared to, let's say, kilometers per hour. We need to keep everything consistent. And you might notice in the question as well, everything is in terms of meters or in terms of seconds. So this has to be consistent across the question. Part C asks us to find the position, xt, of the ball relative to the ground in meters. Position is another word for displacement. X of t is going to equal the integral of v of t dt. So it'll be the integral of negative 10t plus 15. We should be able to calculate this relatively easily. Negative 5t squared plus 15t plus c. Again, we look to our question to find another piece of information that tells us some more information about the position. And we can see we start from a 30-meter high cliff. This means that we started off at 30 meters above the ground. The question specifies that the position is measured from the ground. So it makes sense that x of 0 will be 30. Therefore, 30 is going to equal c as everything else cancels out. Therefore, x of t is going to equal negative 5t squared plus 15t plus 30. And using integration, we're able to start from acceleration, from that get the velocity, and then from that get the position of the ball relative to the ground.